Hello, and welcome to another episode of Defence Uncut, the first dedicated English language Pakistani defense news commentary podcast where we unpack Pakistani military procurements, events, and issues in laser focused detail so that you build an accurate and informative big picture. Over the past several weeks, we really delved into why the Pakistan Air Force should develop an armed drone or unmanned combat aerial vehicle. Last episode, Asim and I discussed how Pakistan's defense industry was primed to undertake this project, but we missed Arslan's perspective. And this week I'm happy to announce that Arslan will unpack a less known but equally important aspect: data links. In short, the data link architecture necessary for UCAV operations is quite different from the data links we're using today. Link 17, for example, was designed to distribute sensor information and enable operators across fighter aircraft, special mission aircraft, and other platforms to make decisions by all seeing a common reference point. But the data links needed for UCAV operations, and essentially the future of air warfare, are quite a different beast. Arslan will discuss this in much more detail in this episode, and together we'll showcase how Pakistan could potentially develop this new hardware and software stack. Arslan has also written a report on how Pakistan can do it in more detail on our main Kuwa website on quwa.org or kuwa.org. So if you're a Kuwa premium subscriber, you'll want to check it out. So hi Asim, Arslan, how are you?
Yeah, good to be back.
So before we get into the main topic, I thought we could walk through a few news stories from the week. So the first thing is the JF-17C or Block 3 made its debut at the 2025 Royal International Air Tattoo. It continues an ongoing tradition of the JF-17 showing up at this particular event. Any thoughts from any of you on this?
Yeah, so this might come off as something that is not an issue. This is something that has bothered me my entire life, and that is that we as a nation have a problem with getting the Pakistani flag right. So I'll give you an example of this. Go out on 14th August or 3rd March or whatever and go on the street and look at the Pakistani flags on sale. You are going to see all kinds of proportions for the crescent and the star and all sorts of weird positions, scales, and it's just annoying. And these are not just subjective interpretations of a flag. These are wrong. And let me tell you why. So I've thought a lot about this. So you can go on to Google and you can search for this official Pakistani flag design. And what will come up is a resolution passed by the Constituent Assembly of Pakistan somewhere around between 1947 and 56 or whenever that assembly was dissolved. And it has the exact proportions on how to draw the official Pakistani flag. I'm not going to read the entire thing, but I'll just read the first few lines just to tell you that it's absolutely codified in text on how to make that flag. So I quote, "Draw the diagonal from top right-hand corner to the bottom left corner of the green portion. On this diagonal, establish 2 points A and B. Point A at a distance equidistant from top right and bottom left-hand corners of the green portion." So it's an entire paragraph that goes on and tells you exactly what the official flag needs to be. And the shame is that the flag on the PAF JF-17C was all wonky. Like, it wasn't the official proportions of the flag. And that's kind of disappointing to see from the PAF, which is the official government-sponsored air force of the country. So that's just a pet peeve I have, and I just wanted to get it out.
Okay, sounds good. This is a completely different point to the one you made us see. But I think is another good sign in terms of the J-17's longevity from the PAF's standpoint. We'll have a series of articles coming out throughout this week where we start to also delve into systems warfare as opposed to platform-centric thinking. And just revisiting some of our earlier thoughts regarding the JF-17, I actually do believe that the JF-17 platform has all the ingredients to be a long-term asset within the PAF, even through new built units, simply because when you're engaging in systems level thinking, which we're also going to get into more detail in relation to data links, it's less about the individual platform and more about like the cumulative capability you're bringing into the air at any given point. So the thing I wanted to really highlight was that, even on May 7th, when we had that massive air clash between the PAF and Indian Air Force, in all likelihood, a relatively high proportion of the PAF fighter aircraft in the air on that night had an active ESA radar. And really, it could have been, I wouldn't be surprised if, given how the PL-15 was very much a central munition deployed in that operation or that initial night, that potentially at least 50% of the PAF's aircraft on that night had active ESA radars. And I believe like that level of scalability and that capacity to bring that many units with that kind of advanced radar, with all sorts of resiliency against electronic warfare jamming, the extended range could only have really been possible if you had a platform like the JS-17, which provides you that low-cost, scalable platform to be able to procure and build in numbers. So I find it, I think, interesting that its role within the PF has both changed and unchanged. Like it would still be that lower cost, medium capability platform through perpetuity, but because the electronics and all those subsystems are constantly changing, it's still constantly advancing with the pace. So Arslan, any thoughts on RIAT?
No, not particularly, to be honest.
Okay. Next news story, the Pakistan Army purportedly starts receiving Z-10 ME attack helicopters. So we've had some reports both on social media and a few voices that I really trust in the space also basically confirmed the delivery, which is why I started talking about it as well. So I think overall the delivery is probable. It's basically the only option available to the Pakistan Army Aviation Corps at this time. But I think it's also worth remembering, just the Z-10 ME's background in relation to the Pakistan Army. So this platform, the ME, was actually revealed like really shortly after the Pakistan Army signed the T-129 order. And it's in my view, which you can find in some past school articles, I believe that the Pakistan Army had been looking into the Z-10 ME long before the T-129 program fell through. So just a few things to note. If you look at the improvements that they asked for from the original Z-10 that they tested back in 2015, you'll notice that there's a very, very strong emphasis on like anti-armor, desert operations, and durability, which is really what the 1Z Viper, which fell through much earlier, brought to the table. And the Z-10 ME, it basically all the things that the Pakistan Army had apparently asked for seemed like specific inputs that would make the Z-10 ME a lot closer, in my opinion, to the AH-1Z Viper than it did to the T-129. So I just found it would be basically weird for the Pakistan Army to talk to CAIC about improving the Z-10 while it was also talking to TAI for the T. And if you look at their capability sets across both these attack helicopters, they're a bit different. So the Pakistan Army, when it evaluated the ATAK, it tested the T-129 for things like high altitude operations, endurance, range, and durability from the standpoint of like being able to like be maintained and stored in like less prepared areas. So the environment and operational situations were very similar to what you would expect to see in places like the tribal area, the northern areas, and Kashmir. Whereas the Z-10 ME, it was clearly locked in for operating in like desert areas in a much more contested environment. It has like integrated ECM jamming, better sand and particulate filtering, upward exhaust, and so on. So in that sense, and also if you look at the Chinese product catalog, you'll notice that they already have a helicopter that's similar to the ATAK, which is a Z-19, which the Army also evaluated, but didn't really select at all. So, and some of the discussion points coming out of social media in relation to Z-10 ME is that it'll be inducted on the eastern side, whereas the Cobras for now will be relegated more towards the counterinsurgency role. So I think there's that prospect potentially in the long run where the Cobras could one day be replaced by an ITAR-free T-129 with Turkish engines. So the Pakistan Army can continue maintaining that high altitude, long endurance attack helicopter capability that they originally sought with the original T-129. And another interesting point in relation to the Z-10 ME is that it's now interesting that the Pakistan Army has like a modern Chinese platform for each of its core requirements. They have like the VT-4 tank, H-15 howitzer, the A-100 guided rockets, the CH-4 drones, and the FM-90 short-range air defense system. So you look at all these pieces, there is that I would say incentive, but I would actually hope it becomes an issue of urgency to organize those units and systems into like more of a combined arms group type situation, especially when you have single sourced the core platforms and all of them sort of been designed around network enabled warfare already, that you can start leveraging that. And it's very interesting that the Army already has like the light commando battalions, which provide that highly responsive specialized infantry capabilities. So it's an issue of like potentially building these other pieces around them in whatever configuration you need for the environment that those LCVs would basically operate in. So yeah, just my thoughts on the Z10 ME. Any thoughts from any of you?
Yeah, so I mean, initially the reason for rejection was just insufficient engine performance and engine hand filtering and whatnot. But the inclusion, so what they've done is, of course, they've improved the engines, but they've also made it way heavier, right? Like you're carrying a ton of new equipment, and it's pretty clear like 90% of this equipment wouldn't be needed for counterinsurgency ops. That sort of stuff is very clearly geared towards high survivability in really contested environments, like the ones these aircraft would face in India, Indian mobile air defense batteries and whatnot, advancing with tank battalions and all that sort of stuff. So it's pretty clear these were never intended to be for counterinsurgency ops, because if they were dedicated and primarily counterinsurgency focused, the focus and the feedback would have primarily been, look, we want something with better hot and high performance with more payloads, but we don't need any of these extra bits. You don't need electronic countermeasures or just even any sort of real electronic countermeasure ability when you're fighting guys with RPGs and AKs.
Absolutely. So next piece is, and it's something I brought up as well here, there's a new shift in the industry towards basically jet-powered loitering munitions. So you have like, for example, MBDA, they recently revealed their one-way effector. L3 Harris revealed the Wolfpack, and Anduril revealed the Barracuda 100. So what these basically are, they're essentially small, sub 100 kilogram cruise missiles. And what I found really interesting was that these are basically designed similar in size and concept and range to things like the Kajam V3 or Azub 81 LR, which we're basically developing within Pakistan. And we had like a discussion in our articles last week about like the adoption of loitering munitions and how that will become more important. I believe we had like a previous episode where we touched upon it. But just as a point of emphasis, I think really the Pakistan's military planners should be thinking more along the lines of what MBDA and L3 are doing here in terms of pursuing these jet-powered loitering munitions. So for example, the L3 Wolfpack, it can be configured as either an attack munition or as a jamming decoy. And there's a great opportunity here because Pakistan already has the designs on hand, either through the Kajam V3 or the Azub 81 LR, where they can, or even the Sarfarosh platform as well, where they can try repurposing them into these, highly scalable, low cost, quick to produce and deploy mini cruise missiles for like a huge variety of roles, right? And I think that's where ideally their focus should be pivoting towards, as opposed to strictly relying on your Shahed style, piston or electrically powered loitering munitions. Any thoughts on this from the two of you?
Yeah, so I just wanted to talk about the possible industrial aspect of going for something like this. Now, obviously, if you want to build loitering munitions, you're going to build them in the thousands, right? You're not going to build 100 or something like that. So there's an industrial need for turbojets or turbofans for these things. Now, this begs the question, why can't these be produced by a private company in Pakistan, right? Why can't we have a Pakistani version of JetCat, right? And once this company or this hypothetical Pakistani JetCat is established, these loitering munitions aren't the only things that they will power, right? There's a huge hobby market that this company could tap into. There's tons of other things as well. There's an export market just for turbojets. Now, I do want to point out that there has been a recent trend in the SPD organizations to start quote unquote private industries. An example of this is Qaswa Industries, and if you look closely at their product catalog, it's basically what GITS is selling. So, and for those of you who don't know this, but GITS is basically a marketing company for NESCOM. And Qaswa is also just, acting like a front or like a different company that is selling products that are being made by different organizations within NESCOM. So when we say private industry, we don't really mean, a production line set up by NESCOM, right? Because that still has all of the problems that come along with operating a state-owned enterprise, right? There is no incentive towards profit, right? The orders are limited to whatever the orders are given to these strategic organizations, right? So these aren't really private industries. These are just production lines set up by SPD organizations. And of course, this is like maybe a tiny, tiny step in the right direction, but this is not really what we mean by private industry. Right. So, for example, when I say a private company, I mean someone like Millet Tractors in Lahore, right? They have a huge factory that makes tractor parts. But I know they're not tooled or equipped to make turbojets. But I'm saying a company like that could potentially manufacture thousands of turbojets, and that could serve as an input to whatever product NESCOM or these organizations are making. So I think that's really important for, the development of these loitering munitions. This is like a great opportunity to set up a private industry for, critical inputs for things like these.
I agree. And I think one thing to really shout out here is that the turbojets required for these loitering munitions are like the simplest, lowest powered ones you would need on the market. So this is something that even I believe NESCOM from its internal development has already crossed that threshold a long time ago. Like they're in the realm of, your 3 to 4 kilonewton engines already. So for them to go and to provide a design for like a sub 1 kilonewton turbojet engine that is basically what you would need for these kind of loitering munitions is not difficult at all. But what they should do is that they can provide the design and the technology transfer or know-how transfer. They can literally teach the private sector on how to basically manufacture them at scale and leave it to the private sector to manage that entire capacity for them, as opposed to taking it on and having to deal with it. And that would essentially give the private sector essentially a very easy, relatively speaking, head start into getting in on this. Like there's no, like the threshold to get in on this isn't high at all. It's like all the ingredients are right there. It's just an issue of like organizing things along the right ways. Any thoughts, Arslan?
Yeah, no, I mean, you guys have nailed it. I think other than power, also the real bottleneck for most is endurance and the lifespan of the engine. But I guess, again, as you mentioned, it's not really a factor for these kind of applications because they are one-way attack drones. So, longevity and lifespan isn't necessarily a major concern here.
Sweet. And now on to our main topic, which is developing a next-gen data link. So just to sort of introduce the discussion here. So I would definitely recommend reading the article if you can from Arslan on the main Google website. Like even the excerpt that we provided will give you a pretty good high-level idea of what we're talking about here. But basically, the data link architecture required for UCAV operations and even the future of air operations where you're going to be leveraging stealth fighters and all this sort of stuff, it's quite different from the way data links have been designed up to this point. So when you look at data link, and this is a high level assessment, Asim and Arslan will get more into the technical aspects of it. But basically, data links like Link 16, Link 17, and like Link 11 and so on up to this point have really been about providing communication and enabling, to an extent, the ability to view off-board sensor information, right? And that has been like the bedrock of what we would typically call, network-centric warfare or network-enabled warfare. But within this environment, it's still relatively a passive exercise. So basically, like you're getting information and the data links are there to help sort of enable things like communication, but the decision-making, the awareness, or the understanding of being able to make sense of the information given to you, it's still left to a human operator to decide. And gradually, with the introduction of things like AI and machine learning and autonomous agents and so on, a lot of that decision-making is being gradually offloaded to your forward-facing platforms like your fighter aircraft, your drones, your munitions even, and who knows in the future how far things can go. And not only that, but you're also working in far more contested environments. So when you look at the rationale and thinking that went behind, let's say, Link 16, for example, you were not dealing with anywhere near the electronic warfare density that you have now, where electronic signals are being tracked relentlessly, threat libraries are being updated around the clock. It's a very different world. And in this new and emerging air warfare environment, you require a very different approach and much more advanced technology. And the hardware stack that you're going to be working with is also quite different from what we had up to this point. So with that, I'm going to hand it off to both Asim and Arslan to basically take the discussion forward.
So before we start, I just want to give some very high level background on RF communication. But Before that, just disclaimer, I am in no way an expert on RF. That's not my area of expertise. I just have a tiny bit of interest in these things. So that's why I know a little bit of this stuff. Right. But this is important stuff that we need to know before we go into the detailed discussion that we're going to go into. Now, RF communication or radio frequency communication, one of the key things that you need to know about is the carrier frequency, right? So what frequency of radio waves you are using to communicate. There's multiple ways of thinking about it, but this is usually thought up, or one way to think about it is as the IEEE spectrum. And you can Google this, and this will tell you the ranges of frequencies that are traditionally given names. So for example, the fire control radars on fighter jets, they're typically X-band. And what that means is the frequency of the radio waves is 8 to 12 gigahertz. So that's what I mean by frequency. So now coming to data links, the most famous data link is link 16. The link 17 is basically based off that, right? And we know that that's, I think, in the 900 megahertz range. That's a very low frequency. And the thing you need to know about frequency is that the lower the frequency, the higher the range, and lower the data rate, right? So you can transmit a lower frequency signal over larger distances, but you can transmit less data per time with that lower frequency signal. So for example, for the link 16, 900 megahertz, and the data rate is around 100 kilobits per second. That's the max data rate. And that's, to give you an example, that's kind of like what dial-up internet speeds used to be. I don't know how many of our listeners remember dial-up internet, but that's the kind of speeds that we're talking about, right? 100 kilobits per second is not a large rate of data, but 900 megahertz, it allows you to transmit those signals at longer ranges. And another thing that to keep in mind is that the lower the frequency, the less directional things are. So for example, very low frequency signals can actually bounce off the ionosphere of the Earth and allow you to use radars beyond the horizon. And that's how early warning radars work, right? Because obviously they're not line of sight, and the way they operate is by reflecting radio waves off the ionosphere of the Earth. And now, as opposed to low frequency stuff, there's high frequency stuff. So a great example of this is something called the multifunction advanced data link. And Arslan talked about this in his article, and we're going to talk about this in this podcast as well. That's the data link that was developed especially for the F5. And that's a very high data rate and a very high frequency link. So it operates in the KU band. And what that means is 12 to 18 gigahertz. So remember, link 16 was 900 megahertz, and this is 12 to 18 gigahertz. So this is a huge difference, right? Now the data rates are probably classified, but you can imagine with the kinds of capabilities the F-35 has, the data rates are very large and allow streaming of HD videos and stuff, right? So the data rates are really high compared to link 16 or link 17. And the F-35 uses phased arrays to transmit and receive data. And because this is a very high frequency, I shouldn't say very high frequency because that means a specific thing. Because this is a relatively high frequency signal, the beams that are generated for the system are directional, and they can be steered. This allows them to have a low probability of intercept, or LPI, as is famous in stealth terminology. They're obviously jam resistant, and because you're able to compress the beam into a shorter, width, you can pump more power and increase the range for the same amount of power. But these systems only operate at shorter ranges because basically the higher the frequency, the more the radio waves attenuate in the Earth's atmosphere. For example, link 16 might work, I don't know the numbers, but maybe hundreds of kilometers. The metal will not work at those distances. Maybe it'll work at 50 kilometers. Maybe, I don't know. The numbers are probably classified, but it's going to be much less than that. Now, another dichotomy is encryption and link robustness versus data rate. Now, we already talked about frequency versus data rate, right? So let's say you have some amount of available data rate. Now you can choose to dedicate some part of it for link robustness and encryption. So for example, suppose your frequency allows you to send 100 bits, 100 pieces of data every second. I'm just making up a number. So if you want very little encryption and very little robustness in your data, maybe 90 units of that data are actual data and 10 are parity bits and encryption stuff. But let's suppose you wanted to have your link be very robust and highly encrypted. Maybe only 10 of that 100 pieces of data is actually data, and the other 90 is dedicated to encryption and link robustness. So roughly speaking, those are the kinds of things that you need to keep in mind. So just to summarize again, low frequency, long range, lower data rate. High frequency, short range, higher data rates. And if you want more encryption and more link robustness, you will have to sacrifice some of the data.
Thank you. Arslan, based on that, I would like to really get an understanding of, one of the things I noticed in your article, you sort of just spoke to this tension between the air-to-air and air-to-surface roles required of like a UCAV and how that would basically influence your data link, architecture. Can you start delving into that?
Yeah. So in terms of this, in terms of your question, and it's going to be a sort of like monologue, quite around whatever you want to call it. I've tried to define stuff and also give examples where I can. So in terms of this contradictory requirement, you can think of it like the operational envelope of a modern combat aircraft, something like a 5th gen fighter or a high-end UCAV, will impose like ridiculously contradictory requirements on its communication systems, because you've got the need to like collaborate, share sensor data, or achieve have network situational awareness in a fluid combat, air-to-air combat requirement. You want something robust and high capacity and also a really resilient data link. Whereas on the other hand, you've got the need to penetrate like heavily defended airspace or strike or ISR missions, mandating like an extreme level of stealth. And this is the one area people kind of ignore. When you think about stealth, you think, oh, really stealthy airframes, low observable physical stealth. But people tend to really, really overlook electromagnetic stealth. And these emissions are a real nuisance, which I'll discuss in a minute. And this creates the fundamental tension, right, between a loud data link mode and like a optimized for connectivity and jamming resistance, and a silent mode, which is optimized purely for covertness. And so resolving this is like the key tension here. So if I move on here and I just discuss the sort of this loud and silent data links, we'll first discuss the loud air-to-air combat and network-centric combat mission focus. So in the BVR arena, combat takes place at like ridiculously long distances at times. Missiles, 150, 200 kilometers or whatever. And with time, this is only going to get greater. Pilots and pilots and crews won't be able to see each other's aircraft, right? So you're no longer worried about the kinematic performance of an individual platform. And instead, modern air combat is a function of superior information and networked collaboration, right? The ability to see and understand what you can see, and also act first. And this is like really, really dependent on the seamless real-time exchange of a ton of information and tactical data among assets. And in this is where the sort of loud data link comes in. It's the key enabler, sort of. And this is a really good way to break this down is think of it as like a team sport, right, where everybody shares what they see on a single like live digital map, like Waze. Like it's such a great example. If you've got Waze, you go on there, you report what you see, and everybody in the area knows that, okay, there's a police officer there or there's a camera there. And the primary function of such a data link is to increase mission effectiveness by providing superior situational awareness and also enabling machine-to-machine sharing of target and threat information. And for 5th generation aircraft and other really advanced network systems, it's not like a luxury, it's a core design feature. And these platforms will feature avionics that are really heavily integrated with each other. This is something I'll discuss later, is like legacy data links versus modern data links. But this is a real key differentiator here, is these are like really, really well integrated systems. Like one of the key selling points talked about with the F-35 is sensor fusion. And this is kind of like the human brain combining information from our eyes and ears to create like a complete understanding of our surroundings. The aircraft's computer does the exact same, merging the data from like radar, cameras, and other friendly forces to build a single comprehensive view of the battle space. And this process of sensor fusion is like ridiculously data intensive and highly sensitive to latency. This is where the data link comes into it, because the function of this data link, it must be like a really high bandwidth pipe capable of transmitting large volumes of data, including radar tracks and platform status, weapons data, health, all these kind of rubbish, to then build a common operational picture among the entire force package. And that common operational picture is like essentially that shared live map that all friendly forces can see, showing the location of allies, enemies, and other critical information. And to be effective in a contested environment, this loud data link must be exceptionally resilient. It must possess really strong anti-jam capabilities to be able to resist enemy electronic attacks. And legacy systems like Link 16, and also one thing, you guys may, this is a Pakistani-focused podcast and whatnot, so we do use Link 16 in Pakistan, but we also use Link 17. And at times, I may interchange between Link 16 and Link 17, but effectively Link 17 is very heavily influenced and based off of Link 16. So whatever applies for Link 16 probably applies for Link 17. So as I was saying, legacy systems like Link 16 and probably by extension Link 17 achieve this through techniques such as frequency hopping. And this is where the transmission rapidly cycles through a wide range of frequencies to make it difficult for a jammer to concentrate power on any single channel. And this is like having a conversation that jumps between thousands of like phone lines every second, so that an eavesdropper trying to block the call would be unable to keep up. And the network architecture must also be as robust. It must also be as robust. And modern data links are designed to be nodeless or operate as something known as a MANET, or a mobile ad hoc network. And this is where each aircraft acts as its own like router, allowing the network to form and dynamically heal as platforms maneuver in combat without reliance on a single ground station or like a hub. And this is something that's really, really key with Link 17. There's a real reliance here on a central ground station, which is quite vulnerable. So, but back to what I was saying, this ensures that the loss of like one of the nodes doesn't cause the entire network to collapse. And this is a critical attribute for survivability in a peer-level conflict. And therefore, it's imperative that a data link that is powerful, persuasive, persistent, and also prioritizes connectivity and high data throughput above all else. I know I've said a lot, but back onto the silent side of things. So while a loud data link is essential for collaborative combat and is kind of like the arch enemy of stealth operations, the primary advantage for low observable aircraft is its ability to delay or deny detection by enemy sensors, allowing it to operate and penetrate in contested airspace and strike like high value targets with a degree of surprise. Therefore, any sort of electromagnetic emission, including like data link transmissions, can be intercepted by enemy electronic support measure systems, potentially compromising the aircraft's position and negating its stealth advantage. And this is why emissions control is such an important aspect of modern combat. And this is something I go further deeper into my article as well. And for missions such as like SEED or Deep Strike or Covert ISR, maintaining strict MCON is essentially like it is paramount. Like essentially you're going radio silent. And this also necessitates a silent data link mode built on the principles of low probability of intercept, LPI, or low probability of detection, LPD. And these are what these are. LPI and LPD is a set of techniques that make it really difficult for a radio signal LPI and LPD are a set of techniques designed to make a radio signal as difficult to find and exploit as possible. The core principles here are to reduce the signal's energy density to a point where it's buried in the background of the RF noise floor. I think of it as like the constant low-level hiss or static present in the radio spectrum. And this is achieved through a combination of methods, you could say. One of them being low transmit power, right? Using absolutely the minimum power required to close that communication link. Or you could also look at spreading the signal among the spectrum, or spread spectrum operations. And this will spread the signal's energy over a very wide frequency band, which reduces its power on any single frequency. Think of it as like taking a piece of toast and spreading butter on it to the point where on some bits you might have butter that's harder to see because it's spread far thinner. Silly example, but an example nonetheless. Well, you can also use advanced waveforms, right? Designing waveforms that lack the distinct spectral features of conventional signals. For example, using like cosine pulse shaping instead of traditional modulation techniques eliminates the sharp spectral lines that are easily identified by intercept receivers, and this makes the signal appear more like random noise. Also, the most crucial low probability of intercept or detect technique, and this is something I believe Asim might be able to touch on as well is directionality, right? This is one really, really important thing. And for airborne platforms particularly, is by using highly directional antennas such as phased arrays, you're basically narrowing the transmission energy into like a very narrow pencil-like beam aimed directly at the intended receiver. A phased array antenna is like a sophisticated spotlight for radio waves, you could think, instead of like a single bulb. And it uses like a large grid of many, many small antennas that can be coordinated electronically as opposed to mechanically to aim a precise beam of energy without physically moving itself. And this prevents the signal from radiating in areas you don't want it to radiate, like where it can be intercepted by adversaries. And this is where MADL, or the multifunctional advanced data link, comes in, right? This was developed for the F-35. It's like the cream of the crop in terms of LPI tags of data links, and it employs fast switching phased array antenna assemblies to create that tightly directed radio signals in the Ku band. And this allows like a flight of stealth aircraft to share data covertly while maintaining their low observable posture. And the future of like the next generation of LPI LPD technology is even more sophisticated, using like with key focus on AI stuff as well. And there's one last technique I want to touch on, and I'm going to pass it back over to Asim to see if he wants to say anything about the directionality before I take it back over. But you've also got generative adversarial networks as well, and these are creating waveforms that actively mimic the statistical characteristics of the sort of ambient RF environment. And this makes them virtually indistinguishable from a naturally occurring noise. A GAN can be imagined as like a competition between two AIs. Like you've got like a forger, and I believe I touched on this as well, but you've got a forger that tries to create like fake signals that look like real background noise, and a detective that tries to spot the fakes. And they compete for like millions of rounds until the forger becomes so skilled that its fake signals are identical to the real noise. And this creates like the ultimate stealthy communication. Yeah, so effectively the mandate for the silent mode is clear, right? Is to be as electromagnetically invisible as possible. Asim, do you want to discuss anything about the directionality of these sort of links?
Yeah, I just want to clarify one, or just re-emphasize something I said earlier, and you talked about a lot, and that is why directionality is useful. So because of the use of phased arrays and high and frequency carrier wave, like in the metal, your beam is, so the way radio waves are transmitted and received, they create, so this depends on the kind of antenna you're using, but they create a radiation pattern around your emitter and receiver. So if you have like a traditional antenna, like a dipole or something old, that's not a phased array, importantly, and you have a lower frequency signal, you are going to create a radiation pattern that basically goes almost everywhere. You can make the antenna directional by using antenna design, but there's only so much you can do because of your traditional antenna design and your low frequency. And that's what Arslan meant by allowed data link, as opposed to something that is more directional because of the use of phased arrays and a high frequency carrier wave. And as Arslan said, what you're essentially doing is you have lots and lots of tiny radars, and they're transmitting radio waves. Now, the thing about any kinds of waves is they can interfere constructively or destructively, right? So they can add up or they can cancel, roughly speaking. And by using some fancy math and fancy electronics, what you can do with these lots of tiny radars is you can artificially steer the beam that you're generating with your tiny radars. And that's how phased arrays are able to steer their beams. Now, what's the real benefit of this? Or one of the real benefits of this? Suppose there are two aircraft that are flying in formation, but they're very far apart. So let's say they're maybe 20 kilometers apart. Now, aircraft A knows where aircraft B is, so it points its data link beam towards that aircraft, and that aircraft B points its beam towards aircraft A, right? So they create a data link that is very directional. So the radiation pattern that these data links will have will be very narrow. And what that means is if someone wants to, or if an adversary wants to intercept or, listen in or degrade that data link, they would literally have to get in between these two aircraft. And that's very hard to do. First, they'll need to know where these aircraft are, and then they'll need to get between, like literally on the line connecting these two aircraft, right? And that's what gives these kind of directional beams their strength in terms of jam resistance and being LPI and LBD.
Yeah, so I'll just quickly summarize on that sort of little monologue I went on. So the operational requirements for the loud and silent modes are in direct conflict, as I just explained, creating that fundamental tension that can't be resolved with a single monolithic waveform. So again, you've got like directionality versus connectivity. A loud air-to-air combat data link must be omnidirectional or have a very wide sort of beam to maintain that network connectivity between multiple highly agile and maneuvering unpredictably aircraft in a three-dimensional space, or a silent link by contrast, which must be narrowly directional and point to point to prevent interception. You've also got the other issue of power versus stealth, right? The loud link requires a ton of power to provide robust anti-jamming capability, allowing it to burn through enemy jamming signals, whereas with stealthy ones, you really don't want that sort of ton of power. This high power makes the signal easy to detect and locate, whereas the silent link must use the lowest possible power to remain below the noise floor, which makes it far more susceptible to jamming. Also, in terms of network topology, the loud mode requires a many-to-many sort of Manet topology to support a large dynamic force package, whereas a silent mode is optimized more for a one-to-one or a one-to-few topology, such as communication within like a small strike package of stealth aircraft. So the tension isn't just technical, right? It's also tactical. A pilot or a UCAV operator makes like a conscious decision when switching between the modes, trading stealth for enhanced situational awareness and network lethality. An aircraft on like a covert ingress mission will always want to operate in silent mode, or mostly want to operate in silent mode. And if it is detected or decides to engage in like air combat, it must transition to like a louder mode to be able to coordinate with wingmen and other assets, far looser MCON and whatnot. So the TDL architecture must be able to support this tactical decision instantly and reliably. And a system that is only like a little loud or a little silent, something that isn't perfectly optimized, will fail at both missions. It must be optimized in terms of performance in two different and distinct operational states, right? Both are in this contradictory operational states, and this is a challenge that demands effectively a new architectural approach. So I will hand it back on to Bilal now for the next questions.
Thank you. That was a very technically detailed discussion, and I think we'll be unpacking that through an article this week to try to maybe connect it to how it would apply in the real world as well, and also to basically connect it also how in terms Pakistan could develop and think about these things in its own operational practices. But that being said, I want to now sort of pivot in what Pakistan can do to develop this sort of architecture and what that architecture would look like. So for example, the sense that I'm getting is that we're looking at two fundamental modes here, right? One for the air-to-air, one for the air-to-surface line. And the other part of it is that they seem like, can this be done through one hardware stack and platform, which can be then, through software and other mechanisms, provide multimodal capabilities, or is this going to require a pretty complex, integrated hardware element, which is going to have to use different types of subsystems, basically? I think that would be of interest to, let's say, our industry listeners, because it's an opportunity where either someone can come in and provide and take ownership of that development, or others or a group of companies can come in and sort of try to tackle one specific input within that. And the other side of it is that, how are we going to deal with things like backwards compatibility with the data link architecture that we already have? So it's not just Link 17 in the PAF, we also have Link Green within the Pakistan Navy, which, it's interesting because I just want to just slight tangent, but one thing I noticed when I was reviewing some of the RIAT documentation, like the marketing documentation, was that Saab said very early on that if you didn't have a link, like a data link already, they would either provide you with a proprietary one or basically help you develop one. And if you notice, recently Thailand, or I believe it was Colombia, one of the two, and basically as part of their Gripen EF contract, one of the offsets Saab is providing is to help them develop their own data link. And I just found that to be very interesting, because I'm just wondering, did the PAF ever take advantage of that offer all the way back, right? And then on the other end, when you look at Link Green, that was developed between Nescom and Milsoft from Turkey. So you have these very different data link architectures running around as well that could be of interest in moving forward. So I would love to know, like, is there an avenue for backwards compatibility and how that would look like as well? So I'll hand it off to one of you to start answering those.
Yeah, sure. So I'll take it over from here if that's okay. And I think first to your first question, I think a really good way of dissecting that would be comparing it to Link 16/17 and show how it's different. I will also pass it over to Asim for this section as well, and as I know he's got some good talking points as well. So just benchmarking it sort of against Link 16, because we've got a lot more to talk about there. To fully appreciate this architectural challenge sort of creating this dual mode system, it would be quite visible here. So the sort of legacy standard, right, which is Link 16, it's basically been the cornerstone of like tactical data exchange for NATO and allied forces, providing the sort of digital backbone for command and control. And it reflects the design priorities of its time, right? Is creating a secure and resistant network for a large number of separate platforms. So just some background on Link 16, right? So it operates in the L band, as I mentioned, 960 megahertz, and is structured as nodeless. The broadcast network's sort of setup is using a time division multiple access. In a TDMA scheme, the network capacity is divided into recurring time slots, which are allocated to different participants to transmit their data. And this is kind of like a single lane road where traffic is managed by like giving each car a specific time slot to pass, preventing collisions and making sure that everybody gets a turn. And with this architecture, it allows many users to share the same network without interfering with one another. And its primary ECCM or anti-jam mechanism is its rapid frequency hopping capability, where the transmission jumps between and across over 51 different frequencies at a rate of thousands of hops per second, combined with like a robust encryption setup, makes the link increasingly difficult for an adversary to effectively jam or spoof, which was a key requirement for operating in a contested environment. However, on the other hand, right, the very features that made Link 16 like revolutionary in the 1980s now make it a significant liability for these fifth generation platforms, because you've got three sort of key fundamental limitations here, right? You've got low bandwidth and high latency. Asim touched on this as well. Is Link 16 was designed for exchanging like pre-formatted low data rate messages. It's like maximum theoretical keyword theoretical here data rate is like 115 kilobit per second, I believe, with practical throughput often being much lower. And this is like orders of magnitudes below what is required to share the fused sensor data of like higher resolution imagery and video streams and whatnot generated by modern aircraft. And also the TDMA structure also introduces inherent latency, which is a disadvantage in critical time sensitive targeting cycles, like earlier with like air-to-air combat via a UCAV. Like you can't do that because you've got inherent latency here. And then you've also got the lack of scalability, right? The network architecture has a finite number of time slots. It's not infinite. So this means that you've also got a theoretical limit on the amount of participants it can support. And it's also not scalable either to meet the exponential growth in data exchange demanded by future network-centric concepts, including like swarms of UCAVs and multitude of sensors. And the biggest problem here for this application is also the compromise of stealth, right? And this is the most critical flaw for an LO platform, because Link 16 is an omnidirectional broadcast by design. And this means that it transmits with high power in all directions, like a lighthouse sort of. And this ensures that everybody, however, because again, by design, right, it ensures that participants over a wide area can receive the signal. However, for an adversary's ESM system, a Link 16 transmission is like a very, very powerful electronic beacon that instantly reveals the presence of any aircraft transmitting, and it can be used to triangulate the precise positioning of transmitting aircraft as well. And this completely negates those stealth characteristics, and it's for these reasons as well that Link 16 is it will remain an essential for communicating with like legacy older aircraft, but it can't be the primary data link for a stealth fighter or a UCAV operating in contested airspace. And this is where MADL came in, and the multifunction advanced data link, and that was developed specifically to address the shortcomings of Link 16 for stealth aircraft. The MADL is effectively the current benchmark, or the cream of the crop, as I mentioned, for a silent TDL, right? It's effectively a core component of the FP5's sensor and communication suite. So it's designed from the ground up for LPI, LPD operation, and it's the sort of the architecture of it is sort of the antithesis of Link 16, right? It operates in the high frequency KU band, and it employs faster switching, arrow beam, and highly directional transmissions. And as Asim said, there's drawbacks to this as well, and I'll let him touch on that in a minute. But it's this is all made possible by a set of phased array antenna assemblies, or AAAs. And these are integrated into the F-35's airframe. And these antennas can electronically steer a pencil beam of radio energy with extreme precision, making sure that the signal is only sent in the direction of the intended recipient. And this sort of high directionality is the primary source of its stealth, right? An adversary, as Asim said, would have to be in direct line of sight between the two communicating aircraft to even have a chance of intercepting the signal. And this is then complemented by other like LPI techniques like frequency hopping, waveforms, and dynamic power control to provide that high throughput and low latency communications while remaining electromagnetically covert. Now, this allows like a flight of F-35s to securely share their fuse sensor data, creating a detailed, unified picture of the battle space among themselves without alerting the adversary to their presence. However, again, this is the problem. The greatest strength is its directionality is also its most significant limitation. It's really optimized for intra-flight, like strike package communication. Because it effectively creates a secure but isolated communications bubble. It's not designed for that broad network-centric communications. It's not designed for that broad network-centric communications like Link 16, like between dozens of dissimilar platforms. And also the other aspect here is the technical complexity of such a thing. MADL is like very tightly integrated into antennas and avionics, which makes it really expensive and also really cumbersome to fit into other platforms. And in fact, there was a upgrade program for the F-22 to retrofit it with MADL, and this was effectively cancelled because of these limitations. And this again highlights the difficulty of expanding MADL's network beyond its native platforms. So this effectively creates like a stark choice, right? Like either you have the broad but not stealthy connectivity of Link 16 or the stealthy but isolated networking of MADL. Neither system on its own can satisfy the full spectrum of operational requirements for the next generation UCAV idea that we pitched last episode. This necessitates effectively a new architecture that can harness the strengths of both, but in a sort of single, more adaptable system. And I think, Asim, you've got a bit more to touch on here as well.
Just to add to something that you were saying, so you can go online and read a lot about what's actually inside the aircraft. Even though it's classified, there's a lot of stuff online. So one thing that we've been casually mentioning is sensor fusion. And one of the superpowers of the F-35 is actually sensor fusion. And there's a great paper on this by engineers at, I think, Lockheed Martin. And it goes into detail on how the sensor fusion algorithm on the F-35 works and why MADL becomes important or crucial. So traditionally, or previously, sensor fusion was about combining data from different sensors, for example, infrared search and track and a radar, and providing the pilot with a combined picture of an enemy aircraft track. Then the next level of sensor fusion was through data links, right? So a flight of 2 J-10s, for example. So there's sensor fusion algorithms running on each J-10, and they can share the information between them. So now because they're sharing the combined tracks, so it's really just maybe 6 or 12 minute number. So it's a very low amount of data that they need to share between them, right? Because they're only sharing the result of the sensor fusion, right? So you could possibly do that with something like Link 16, right? But the F-35 goes even beyond this. So there's a problem with this approach. So for example, one of the aircraft gets, for example, jammed or spoofed. So it starts seeing some, phantom tracks of aircraft. Those phantom tracks are going to be copied on to the other aircraft that was not even being spoofed, right? And there are multiple vectors of attack in a system like this because you're basically sharing processed data. So the F-5 goes one step further. It does not share processed data. So a flight of 2 F-5s will actually share sensor data. So this is wholly different from sharing fused data. So it will actually share raw data from the radar and its cameras among all of these aircraft and all of these aircraft's distributed sensors, right? So the sensors so you now have, it's like an aircraft having 2 radars and 2 infrared search and tracks. And then the sensor fusion algorithm is applied on this entire, set of data. So this makes the system more robust. And that's why you need a data link like Matto that can transmit the large amounts of sensor data. It's not pre-processed data. It's raw sensor data. So that's one of the reasons why, Matto was such a requirement, and why, sensor fusion is basically a superpower for the F-35. Another thing that I wanted to talk about, which is restricted to UCAVs, is the dichotomy between link bandwidth and autonomy. So let's say you designed a UCAV to do dogfighting. I'm not saying that's going to be the primary mission or anything. Let's, for example, suppose that we have a UCAV that does dogfighting. Now, you could have a pilot on the ground directly flying this aircraft. So you don't have, a lot of autonomy. This is basically a remotely piloted vehicle. Now, if you wanted to use something like Link 16 or 17 for this, maybe you could transmit those commands, but because of the latency and the susceptibility to being jammed and intercepted, this link will not be very reliable. So, for example, at a critical point during a basic fighter maneuver, you lose the link. And what happens then, right? So you might lose the fight right there and then. So we want to compensate for that lack of, bandwidth and, weakness of your data link with autonomy. So the more things you can do autonomously on a UCAV, the less reliant you are on something like the Link 16 or Link 17. So we need to build autonomy into whatever future UCAVs we are building in parallel to creating more powerful data links. With that being said, UCAVs will need, data links like the Matto to communicate within a flight of UCAVs, for example, right? So you send like a flight of 4 UCAVs for a suppression of enemy air defense mission. Those UCAVs need to communicate A, silently, and B, reliably with each other about the targets and the mission and any other sensor data that they need to share, because they need to have the sensor fusion that is present on F-35s, right? That's the kind of sensor fusion that we should be striving for in our UCAV program. Now, with regards to the hypothetical future link or data link for the Pakistani forces, I would say maybe it needs to be a collection of several systems. So maybe, I don't know, it doesn't need to, mimic the Matto, right? So it could be operating at a lower frequency, or maybe an X-band or 2 to 4 gigahertz or whatever. So the planners in Pakistan need to decide on that. And obviously that whatever that system is needs to be backwards compatible with Link 16, Link Green, Link 17, whatever, because we are going to have those systems operating basically for a very long time. And we need to have that system as a backup as well. But what you could have on, for example, UCAVs or, next generation fighter aircraft is an option to switch off communication to Link 16. So you're basically going radio silent, but maybe you still communicate on your hypothetical high frequency channel, right? So all sorts of these special conditions and, how should I say this? Mission specific things need to be built into this, hate to use the word, but modular data link, right? So, and I know this is going to be expensive because once you go for a system like Matto, you're going to be, dealing with phased array data links, right? And that's going to be expensive and is going to require a lot of investment into hardware as well. Speaking of hardware, a lot of this development in data links can be done or is basically the domain of software. And Arsalan has talked about this and perhaps he'll talk about this more, but there's a lot of, AI, and basically the strength of AI can be used to make things like cognitive data links. And these are so this is something that we touched upon in the previous podcast as well. This is something that NASTIP is ideally suited to work on because they're not a manufacturer or of aerospace vehicles, but what they do have is lots of manpower, lots of buildings. They can get computers, they can get computer scientists, and they can, get engineers. They can establish the infrastructure needed to develop the next generation, like I said in the previous podcast, AI pilot, and the next generation data link system for all of Pakistan's armed forces.
Yeah. So based on the discussion so far, so what would be your assessment of what Pakistan would need in order to develop a next generation data link?
Yeah, so again, as I said, this will be a bit of a monologue. Oh, sorry about that. Yeah, so as I said, this will be a bit of a monologue, but in terms of developing a homegrown next generation data link, we're going to need to. I'm going to tangent here a little bit actually, and talk about the foundational technology, which is the software-defined radio platform, which actually is something we have a ton of work in via NRTC and other organizations. And the entire concept of a dual mode data link is predicated on the sort of software-defined radio technology, right? Traditional radios are effectively hardware designed, and meaning their core functions such as frequency of operation, modulation, type, protocol are all fixed by their physical circuitry. On the other hand, a software-defined radio, in contrast, shifts these functions from like dedicated hardware into software running on like FGPAs or SoCs, and these are effectively really, really powerful reconfigurable computer chips. If you think of it. Or like Legos designed that can build specialized circuits and whatnot. So this shift in architecture is effectively revolutionary, right? It decouples the radio's capabilities from its physical hardware, allowing a single piece of equipment to perform radically different tasks by simply loading and executing different software applications known as waveforms. And so an SDR platform can effectively be reconfigured in real time to change its frequencies, bandwidths, modulation schemes, and networking protocols and whatnot. And this provides like the essential flexibility to be able to create that true dual mode TDL. This same radio hardware could effectively, in one instant, execute like a high power jam resistant MANET waveform for air combat, and in the next switch to like a low power, highly directional LPI LPD waveform for stealthy ingress. And this sort of software centric approach offers that a profound advantage for these kind of applications because it future proofs that sort of communication system, allowing for new waveform capabilities to be deployed through software updates without requiring that costly and time-consuming hardware replacement like Kasim talked about. It also enables adaptations to new and evolving threats in the electromagnetic spectrum. And for the dual-mode TDL, the SDR is not just like a component, it's effectively a fundamental enabler that makes the entire concept possible. Running on the common sort of SDR platform, the dual-mode tactical data link would effectively feature at least like two distinct specialized waveforms, each optimized for those mission profiles, like the silent and the loud one. So you've got the first one, the loud high throughput MANET, and for the air-to-air combat role, and this would effectively employ like a high capacity resilient waveform designed for a mobile ad hoc network. And as I mentioned earlier, this type of network is like self-forming and self-healing, where each node is decentralized, automatically relays data for others. So this sort of waveform would leverage advanced technologies to maximize data throughput and reliably in a dynamic high interface environment. And some of the technology, or I'll focus on two key technologies here, or a couple rather, and that is MIMO, right? Being our first one we'll look at is multiple input, multiple output technology. And this uses multiple antennas to send and receive multiple data streams at once. Like a really easy analogy for this is a team of work is carrying a box, right? So you've got like, instead of one person carrying a box, you've got like 10 guys carrying a box. MIMO is that multiple people carrying that one box, right? Simultaneously, dramatically increasing the amount of data that gets through. And this increases the data rates and also robustness. We've also got coded orthogonal frequency division multiplexing. Now is a mouthful, and this is effectively a really sophisticated modulation technique, which is ideal for challenging environments. Right? Imagine you're shouting a long sentence across a canyon where echoes can garble the sound. Instead of shouting the whole sentence at once, COFDM breaks it into small pieces, sending each piece on a slightly different, like sort of musical note or a frequency. In this example, you're sending it on a different frequency, right? And also adding some sort of redundant information on the coded part, even if the echoes distort some of the notes. The receiver can use the redundant information to piece the original sentence back together perfectly, right? And this makes the signal highly resilient to multipath fading and interference, which is common in airborne comms. Modern MANET waveforms can achieve data rates in excess of like 80 to 200 megabits per second, and providing the bandwidth necessary for sharing fused sensor data and full motion video. You've also got the sort of silent waveform, right? Which is the advanced LPI LPD, and this is the sort of technology you'd be looking at here is stuff like advanced modulation encoding. And instead of conventional modulation, you might use like pulse position modulation, for example, where information is encoded in the precise timing of the pulses, and this is combined with independently coded in phase and quadrature signals. And think of this as kind of like a sort of Morse code where the meaning comes not from the length of the beeps, but from the exact different moments in time where you send them. And this is coupled with like randomized start times within a given time slot, making the structure highly irregular and really difficult for a receiver to recognize. And then that's something I touched on earlier as well. And then on the sort of next mean reducing your signature is, you can use featureless waveform shaping as another technology, and this is employment of like pulse shaping filters, like the cosine stuff I mentioned earlier, and this creates like a spectrum that resembles like band limited white noise, eliminating those distinct spectral lines that intercept systems are designed to detect. And the other thing I mentioned earlier as well is dynamic power control, and the system would continuously monitor the link quality and use the absolute minimum power, transmitted power, to maintain communication. And this is a really crucial feature that is already employed anyway.
Before getting too technical into it, I would just want to like kind of shout out or identify a bit like where Pakistan actually stands in some of these areas. So I know we cannot speak to it in very specific terms because we lack the information, but are there any like baseline signs that would indicate that at least the foundations to take on the required research and development are in place? Like, for example, there is evidently some work in relation to like cognitive SDR technology.
Yeah.
So we know that NESCOM's been developing something for counter UAS operations.
Yeah.
But is that something that can then be developed further and repurposed further in direction to data link technology, for example? The other is, for example, leveraging phased arrays at a higher scale. So we know, for example, with PFX Alpha, the JF-17 upgrade, there have been some studies or mock-ups about the potential use of embedding more phased array, I guess, transceivers along the airframe, for example. We don't know to what degree that has advanced or whether that'll come to fruition, but it's something they have an awareness of and know that that's the direction they need to take eventually. So what is your assessment, I would say, what is your assessment on where Pakistan is in terms of taking on this kind of project? Because this is this is like multiple times more complex than Link 17 is.
Oh, yeah.
Right. This is, if you think about it, this is a platform in of itself. So whereas Link 17 would be a contributing piece towards other platforms and operational elements, this is like an integral actor in its own right that has to be secured, has to be reliable, it has to be versatile in order to be used across the Air Force's operations. So it's not even a small thing anymore. I can foresee that in the long run, it would require like a dedicated sub-force just to manage, basically, because there's just so many pieces involved here.
Yeah, no, exactly. And as you mentioned, and I think this is something a lot more about, is Pakistan has a ton of work on like software-defined radios and all that sort of stuff, right? We've seen NRTC, I believe, coming up with their own software-defined radios, and most of what I've just sort of said relies on the software-defined radio technology, right? And also on the other aspect, you mentioned phased arrays and all this sort of stuff and the work undergoing them. I believe it's been a few years now since we uncovered that Pakistan had been working on its own phased array technology down at the stuff. It's a very core, right? These are gallium nitride based transmitters and receivers and whatnot, designed in-house by engineers at NUST in collaboration with Avirid for the X-band fire control radar, designed probably for the JF-17. And you've also got other work being done on ground-based AFX. So all this stuff is coming into fruition. And just like I said towards the end, right there is, and I'm going to repeat it, is ultimately architecting this dual mode system is a complex system integration challenge, and it requires marrying that advanced antenna physics and powerful, efficient computing, and also more importantly, the highly sophisticated software to create that cohesive system. And here we've got all of the bits, right, but we don't have that software and that cohesive system. I think that's where and that's also going to be the most difficult part, right? And that's where you're talking about this special dedicated force and whatnot, and that's where this is going to come into play, right? Because we've got a lot of the puzzle pieces. I'm not going to say we've got them all. I'm not even going to say they're perfect or they're what's needed, but we've got puzzle pieces. We've got the fundamentals. It's now marrying them all together to be able to work this out. Because even these sort of integral antennas, right? Pakistan has experience with this. The JF-17 Block 3's electronic warfare suite is all designed in-house, and potentially uses antennas slotted into the leading edge flaps of the JF-17. I don't know if you guys have ever seen, but if you look at a picture of a Block 3 in the production phase before it's been painted, you'll see that the leading edge flaps, the inboard ones, are composite, and they are a radome. Actually, they're a radome, and they contain two sets, I believe. Each side contains either 2 or 4 sets of antenna clusters. So these are either going to be, well, to be honest, I can't think of anything other than electronic warfare transmit receive assemblies. There's a ton of experience here, and all of the right experience, except, it just needs to be developed further, and it also needs to be married together. And that's where the challenge lies.
Yeah, and I think that's where, when it comes to the software side, I mean, I think Asim, and just so our audience members are aware, Asim had to quickly step out for another commitment. But basically, one of the things that Asim highlighted was, which are the organizations which are the best suited to absorb all that software expertise and leverage it quickly. And between the ones that we have, I mean, it's very hard to bring in like a large sudden infusion of civilian software experts into NESCOM, right? Due to just it's a tightened down, lockdown environment, and typically, they are secretive in nature, and I think it, they've become relatively adept given their circumstances within the hardware space. So, and even I would say this would extend towards NRTC as well, is that you can task them to deal with the software defined or SDR side of the equation as they've traditionally have. And I mean, that's, if you notice, they're also getting into active ESA radar development as well. So they are developing an in-house competency in terms of being able to design and integrate phased array modules and phased array inputs. So there is that competency there. On the NASTAP side, you also have that, again, similar phased array integration and design element as well. But the advantage with NASTAP, especially when it solicits investments from external companies like Baker Group and so on, is that it is ostensibly much closer to the civilian commercial realm compared to NESCOM. So, and because they have these parks embedded within all of the major cities, they are uniquely positioned to be able to recruit and hire that software talent across the spectrum. It's just an issue of whether they are willing to make that. And I would argue that it is a bit of a pivot compared to what they have been getting into. So a lot of the people that they seem to be hiring they seem to be involved in UAS or UAV development, some aircraft related program, and so on and so forth. But I think if they're able to make this pivot towards software, they could actually become that powerhouse for supporting not just the data link development, but the PAF's other software related elements. And I think, again, like as you said, like the ingredients and maybe even the basic direction is already there. Like you hear them talk about quantum encryption, quantum resistant encryption, AI and machine learning, and this and that. It's just that they need to now commit towards this direction and really define themselves as that piece of the puzzle.
Yeah, effectively. I mean, we've seen like the forces have some decent interest in technologies that would enable this. Like UPA after 2019 launched the Center for AI something, or Centake in I think Nordkhan. So there's some, as I mentioned, there's bits and bobs here and there. It's now they need somebody to really drive that. They need some strong leadership to really drive that. And also, I guess there's a lack of necessity, right? Because we're kind of not really in that operational environment where you really need these sort of really advanced directional links. And to be honest, I think the only time in the near future, or potentially ever, we'll see something like this is through the inductions as opposed to homegrown development. And that's sort of the pessimist in me, being skeptical about our project management skills and our forward thinking and whatnot. And potentially, as I said, the only time we might see these in country is bought off the shelf from China with an J35 bio or whatever. But to be honest, on the other hand, widespread adoption of these kind of things will also come with time. It's not really something that's needed at the moment because we don't have the platforms to support it. So it's effectively something that needs to be baked into the decision making and also any future products, right? And when we think about like PFX, for example, you don't see on the the promotional rubbish that they put out, advanced secure data link or high capability directional data link, anti-jam resistant, all this stuff. You see like, oh, it's got leading edge flaps, or it's got a homegrown Acer. And that's sort of where you've got this issue, right? This is all very, very forward-thinking stuff because of the deep hardware and software level integration, actually. So it's all very forward-thinking stuff, and it needs to be on any operational requirement being put out for a new aircraft or whatever. It needs to be there first and foremost, because it's not an afterthought. It's not something you think of, that, oh, hey, this is what we need, let's add it in, because you can't do that. Anybody designing the future force or the future force structure, they need to really account for this in their decision making and also in their planning. That look, every buy needs to have this like MADL-like data link capability built in from the ground up, and then any other platforms who further induct also need that, because without that from the sort of conception stage, it's not going to happen otherwise. Like right now, it wouldn't happen. The US hasn't been able to do it. Forget us.
Yeah, and one thing you sort of highlighted indirectly, and it also speaks to Asim's point as well, is I can see in order for anyone to pull this off as efficiently and optimally as possible, they would really have to also single source the sensor stack as well. Because the issue is that if in the case of MADL, the advantage that MADL has is that the sensor source for the F-35 is also, although they're different companies, they're all fundamentally come from the US. There's that, at least from the US Air Force and, US Navy standpoint, there's that advantage of knowing that at the most basic core level, there is going to be the compatibility for interoperability. However, in the case of the PAF, you're still in this and I think the PAF directionally, especially under the current leadership, they want to gradually single source the sensor stack, which is why they're getting into, for example, getting NASTAP involved in developing radars, developing, the Airborne Early Warning System project. So they have the broad direction, but the reality is that until that manifests, a lot of their procurements, whether it's coming through China or Europe or what have you, or Turkey, they are basically importing just this array of different hardware platforms, right? So there's going to be an immediate challenge to even bring these forward if you did have like a next generation data link architecture. And I think because of that reality, because we're not doing that, because, to the credit of the US, when it came to MADL and 35 sensor fusion, this is baked in from the very beginning. It still hasn't reached the cumulative vision, but it's definitely flying in that direction. The challenge for the PAF is that if you even did have this next generation data link architecture, and I'm sure they're building towards that, how much of your existing base is going to be able to leverage that, because you have essentially a hodgepodge, of off-the-shelf sensor solutions like your air defense radars for the HQ-9BE, the HQ-16FE, and so on. They're from one source, and then you have your Pakistan Navy's radars are from another source, and then you have your domestic radars. So even with the direction that they have, it's going to take a while before they can get it off the ground from an indigenous standpoint. So like in the meantime, I think, as you said, or as you alluded to, what's going to essentially happen is that bits and pieces of the next generation data link architecture will be inducted, but they will be in these like bubbles essentially. So the government's tweet about China offering the KJ500 AWACS, the J35, the HQ-19, the inherent implication in that package is that because it's all sourced from a single supplier and a single, it's based on the requirements of a single user, which is the PLA, the underlying integration for things like CEC, like cooperative engagement, the stealth grade data link requirement for stealth fighter operations or offensive operations, or even potentially UCAV operations, it's already baked into that. But the challenge for the PAF is that, yes, it'll be able to deploy the capability, but it's going to be basically tied into having to procure very specific platforms from China. Like it's not even the flexibility of being able to select whatever platform you want from China. The issue is that, let's say you want to introduce UCAVs into your picture, the UCAV that you select from China, it has to literally be already compatible with this interoperability layer, right? You just cannot, like a new Chinese vendor can come to you and offer you this great deal on potentially like a UCAV design, but like let's say like something Long March comes to you and says, hey, we have this design, we want to offer it, and it happens. Like there's so many Chinese companies that get into this stuff. The problem is you're probably going to have to source it from Chengdu or Shenyang or something, because that is the platform that the PLA is opted for, right? And that is, I think, the challenge with the PF. It's multi-layer. It's not even an issue of just having to source from China. It's like even within China, you're gonna have to source from very specific suppliers, because those are the ones that the PLA selected. So basically, what's happening with the PF potentially is that in the near term or in the foreseeable future, its offensive leg is going to basically be heavily influenced and shaped by what the PLA itself is doing. And that would explain a lot of a lot of those frequent exercises between the PAF and the PLA. And that's an advantage for sure. The downside is you lose the ability to make your own choices and develop your own platform. And when you do develop your own platform, it's going to take a long time before you can get it to sort of supersede the imported stack.
Yeah, I mean, but one sort of distinction I want to make here, though, is stuff like Madel and systems like Madel are designed to work more closely in terms of like strike packages and whatnot, because as Asim mentioned as well, is they're designed to operate at much shorter ranges with a much less participants. So they are sort of these localized communication links in bubbles, like you mentioned. So potentially what also we need to look at and investigate is the intercommunication or development of some sort of intercommunication or some sort of longer range linked that is still able to carry out, low probability of intercept operations, or able to transmit a ton of information. Again, you've still kind of got that issue here: is do you want low, LPI? Do you want stealthy, or do you want a ton of information being passed from these really powerful, really capable sensors? These sponges of emissions and data. You've still got this issue here, but potentially you're able to work it out in such a way where you've got something that isn't necessarily as highly optimized as these inter-aircraft links, because you don't need it to be, right? These are operating at much longer ranges, not necessarily designed. It's a real problem, and it's something that potentially we can investigate further and potentially discuss in maybe a next episode or whatever. But we're just touching the tip of the iceberg here. There's a lot to talk about, and there's a lot of really complicated physics and engineering that's going to go into this. How we execute this is going to be real killer, because these Madel-like links aren't necessarily going to be your fleet-wide or your systems-wide data link architecture, right? Because there's significant limitations that make it unsuitable for that. But your alternative is also going to have significant limitations. So it's something we can investigate potentially in a further episode.
Yeah, so I mean, that's a great concluding point. And I think one thing that this was a very technical discussion that I personally had trouble following, so I wouldn't blame any of our listeners, but I would definitely not dismiss it, because I would say this is like really a rare glimpse of the kind of technical discussions that would happen amongst the insiders, so to speak. And they would get into even, because they have access to the actual hardware and supplier bases and all that kind of stuff, they would have to get into even more technical detail. But it really does highlight both the difficulty of this. So we kind of framed it that, hey, Pakistan is positioned to take on a next generation data link project. That's true, but we're finding out is that next generation data link itself means many different things, and it would actually comprise of many different data links, right?
Yeah.
So there are some aspects that the PAF is already very well positioned to pursue sooner than later, and it'll probably do so. But what we're now architecting here is like the vision of the communication and information sharing stack itself. And I think the opportunity, as much as it's a difficulty, is that it's another area that Pakistan can just immediately step in and start carving its niche, right?
Yeah.
I think one of the recurring themes from the Pakistani defense industry is that, yeah, they're not a turnkey manufacturer. They're not your cutting edge technology driver, but they do integration really well.
Yeah.
Like this has been the story from the day they had to like pair the AIM-9 to the F-6, right? To the MiG-19, basically. Where they had to like help translate the manuals of the Chinese MiG-19 to the F-6. Integration and localization has been their bedrock of this industry, and it's really the foundations of which has kind of emerged. And it, unfortunately, for one reason or the other, many of which are outside of Pakistan's control, like American sanctions, for example, it sort of had to veer into manufacturing and other sides of the equation. But I think when it comes to the communication and information sharing stack, there is this really unique opportunity to just dive into the integration stuff, pick your niche, leverage the things that are relatively easy to build from a capacity standpoint, even though the work itself is difficult. So for example, software is very difficult, right? That's the reason why the software industry has, gone into the trillions of dollars in value globally. That is true. But the ability to set up the infrastructure to take on software development is a lot less difficult than the cost of setting up the R&D infrastructure for software development for this is a lot less than having to get into like a next generation fighter program. And I think this is an area, in relation to the UCAVs and loitering munitions and sort of thing, that Pakistan's industry is really suited to take on and and get an advantage in. And when you get into systems level thinking, you're now really worried about the things that tie your platforms together, like the data links, like the communication stacks, like the encryption stacks. And I mean, for the Pakistani industry, not only is it such a critical area to master for national security, so I mean, there's so many opportunities here, and I think it's another one of those areas where we're starting to see that Pakistan could build its own unique character in it, but it requires immense amount of work.
Yeah,
No doubt.
I mean, absolutely. There's some investment, not even just some, but a lot of the investment in other areas like phased arrays and development of integrated, those integrated electronic warfare suites, area structures level stuff, like all of that stuff is useful here. So there's some ways of some of that cost will be amortized via the use of these other avenues, but it's not a simple endeavor. It's not an easy endeavor. It will be a very costly endeavor, and it's an endeavor that requires a lot of forward thinking, which is something we tend to lack in Pakistan. No matter how well we do other things like the induction of airborne early warning systems years ago, we will see some moments of genius, but then generally we tend to lack this forward thinking. I know I also mentioned that I would talk about the AI driven data links and all that stuff, but I think we'll save that for a part 2 because this is getting quite long and it will absolutely confuse the life out of you at this point.
Absolutely. So with that, we are concluding the episode. Once again, I thank our listeners for tuning in, and I definitely, especially for a technical topic like this, I definitely encourage you to send us questions at podcast@kuwa.org, and I'll try to get Arslan or Asim to respond to you either through the email or through a future episode. And that being said, I also would love it if many of you can actually start subscribing to our channel so you can stay up to date. And we are going to be expanding the video library on the Kuwa channel as well. So besides the podcast, we are going to be delving into, I believe, it's we've seen that there's a bit of a gap in terms of understanding the technology. We also want to provide you informative video posts on the technology and who's adopting them, how that's being deployed, so you have a better understanding of. So as we go into these more meaty episodes, you have a better understanding of where we're coming from when we start talking about phased arrays and active ESA and that kind of stuff. So once again, I thank you all, and please do subscribe. We definitely see X the number of people viewing relative to subscribers. So we see you. We don't know who you are, but we'd definitely love it if you could subscribe to our channel.
And also, just before we go, give us suggestions for what you want to see as well. If that sort of helps you stay interested, give us suggestions for what you want discussed as well, right? You can drop the suggestions at podcast@kuwa.org or drop them in the comments. We always read the comments. We don't respond, but we always read them. So yeah, that's been that from me today, and hopefully I haven't confused you too much, and I will carry on next episode.
Absolutely. Definitely give us a list of topics you would like us to discuss. Obviously, if we cannot make a full episode out of it, we will put it into our weekly news commentary part of it. If you come across any news pieces that you want us to tackle as well, definitely just either throw them in the comments, email us, or you can even reach out to us through X. So once again, I thank you all. Take care and bye.